Oh my god, we finally did it! We made it to smooth manifolds. A second name for this video could be let k equal to infinity. When we've been talking about ck differentiability, for a smooth manifold, we want things to be differentiable to arbitrary degrees. That's what we call C infinity functions. So all of those k's that we had before are going to become infinity, and C infinity is another name for smooth. So lots of words for the same thing. A smooth manifold, or C infinity manifold, right? C infinity and smooth are the same things. Well, that's a topological manifold together with a C infinity differentiable structure. This is also known as a smooth structure or a maximal atlas. It turns out a maximal atlas has a one-to-one correspondence with a smooth / C infinity differentiable structure on a manifold. Now, what do you get when you order a smooth manifold? So here we have a smooth manifold. It's a pair of objects. You get a topological manifold together with a smooth structure on that manifold. A infinitely differentiable structure on that manifold. And what do those things mean? Well, a topological manifold, that's a set of points with a topology. That topology is Hausdorff, right? Any two points are distinguished from one another. That's another way to think of Hausdorff. There's no points that are stuck to other points. And it is second countable. That's also a topological property. It has a countable basis to its topology. This set is also locally Euclidean. Its open sets are homeomorphic to Rn, where n is the dimension of this topological manifold. And remember that your smooth manifold also comes with a smooth structure. That makes sense? That's how we get the smooth into the manifold. And remember that the smooth structure gives you all of the charts. Charts are open sets together with homeomorphisms that map from our manifold to Rn that are smoothly compatible, C infinity compatible. That means for all I and j, right, pick any two of these charts, and then you take the homeomorphisms and you compose one with another one's inverse. The partial derivatives of all orders of this function, the transition function, are defined. But how is that going to happen if your charts themselves are not smooth? So your charts are now upgraded from homeomorphisms to diffeomorphisms. So now all the functions that we're using to talk about our manifold itself are smooth. Right? We have a manifold, then we have some open cover of it. In some sense, each piece of your manifold is smoothly equivalent to a piece of Rn, and we know how to work in Rn. So we can take our work in Rn and then smoothly deform it back onto our manifold and do that component by component until we know what's happening on the entire manifold. We care about smooth manifolds, one, because it's a rich study in and of itself, but two, it turns out, as far as we can see, nature is smooth with respect to things like general relativity. So if you want to understand nature, you're going to have to understand smooth manifolds. And you get all these interesting properties when you order a smooth manifold. My plan for my next video is to give examples of manifolds and smooth manifolds and compare and contrast and go through all of these notions again in examples. Okay, so thanks for watching, and I'll see you guys in the next video.